Welcome physics people once again to Juddy Productions. In this video we'll be looking at VCE Physics Unit 3 Area of Study 3, focusing on power transmission, and we'll be looking at analysis of a power transmission system. Task number 1. Consider the following power distribution systems. So you have in front of you System A, which consists of a power source of 10 kilowatts and 240 volts RMS, a transmission line resistance of 5 ohms, and in this scenario, we're transmitting with no transformers, that is, no step-up or step-down transformers. And we're comparing to System B. In System B, we also have a power source of 10 kilowatts and delivering 240 volts RMS. We also have transmission lines with a resistance of 5 ohms. However, in this scenario, as you can see, we're using a step-up transformer at the power supply end of the transmission lines with a 1:10 ratio, and a step-down transformer at the load end of the transmission lines with a 10:1 ratio. And for both systems, we want to calculate the supply current, the voltage drop across the transmission lines, the power loss in the transmission lines, the voltage received at the load, the power received at the load, and the percentage power loss. In addition to these calculations, we have a second task. We wish to determine which of the systems is preferable, and we wish to explain why. So let's now investigate the calculations for both System A without transformers and System B with transformers. Okay, here's our simplified circuit. We have a power supply, we have a transmission line, and we have a load. Most questions do with transmission of power will start at a power supply and get you to sequentially work across to the load. Or alternatively, they might give you information about the load and get you to sequentially work back to the power supply. In this case, our starting information is based around the power supply. We're told the power supply generates 10,000 watts. And we also have a voltage of 240 volts. Our very first question is to calculate the current coming from the power supply. So let's give that a go. So there we have it. Using power equals voltage times current, we can work out that current is equal to the power divided by the voltage. Put in my power of 10,000 watts, which is the equivalent of 10 kilowatts, and divided by a voltage of 240, gives me a supply current of 41.67 amps. Now that particular current flows all the way through our transmission lines and reaches our load. The second part of this question, we've been asked to work out what is the voltage drop in the power lines. So I'd like to consider this, if you like, in three sections. We have our power supply, we have our transmission lines, and we have our load. So this next question we're asked to work out what is the voltage drop in the power lines. So as a starting point, we know the resistance in the lines is 5 ohms. We also know the current coming out of the power supply to be 41.67 amps. Now that remains the same across the transmission lines, so that is also the current running through the lines. Now we can use just a simple V equals IR to work out the voltage drop in the transmission lines. So using Ohm's law of V equals IR, where I is the current running through the transmission lines and R is the resistance of the transmission lines, we end up with a voltage drop of 208.35 volts. Our next question asks us to work out what is the power loss in the transmission lines. Now the equation we use to work out the power loss in the transmission line is P equals I squared R. So there you have it, the power loss in these transmission lines, where we have a current of 41.67 amps and a resistance of 5 ohms, comes out to 8,681.94 watts. Our last couple of questions relating to the load. So we want to work out what is the voltage at the load. Now we can work this out using a really common sense approach. We started with a supply voltage of 240 and we've dropped in the lines 208.35 volts. So there we have it. Of the 240 volts that we started with at the supply, only 31.65 volts remains by the time we get to the load. And that's because 208.35 volts has been dropped across the transmission lines. This is not a really great outcome. This is a very large amount of voltage being lost in the transmission lines. And finally, we're asked to calculate what is the power at the load. And once again, this can be calculated using a common sense approach. The power at the load is equal to the power that we started with at the supply, 10,000 watts, minus the power loss in the transmission lines. So what we started with, what we've lost, is what we have at the end. So there we have it, the power load. We started with 10,000 watts. We lose 8,681.94 watts, and we end up at the load with a power of only 1,318.06 of a watt. That can also be expressed as percentage power loss. Sometimes you're asked to calculate that value as well. So let's try that. So of the 10,000 kilowatts of power at the power supply, 86.8% of that has been lost in the transmission lines. Welcome to scenario B, which is almost identical to scenario A. We still have the same power supply, we still have the same transmission lines with the same resistance in the lines, and we have a load at the end. The only difference is this time we're introducing two transformers. The first transformer, T1, has a 1 to 10 ratio in terms of number of turns. When the turns in the primary to the turns in the secondary increases, we call this a step-up transformer. This will increase the voltage, but on the other side it will decrease the current entering the transmission lines. On our second transformer, we have 10 turns in the primary and 1 turn in the secondary. This is a step-down transformer. This will step down the voltage, but alternatively increase the current. Now, as I did in scenario A, I'd like to consider this as sections or segments. First of all, we have information about the power supply. We have information about the step-up transformer located at the end of the power supply before the long-distance transmission. We have information about the transmission lines. In this case, we know there's a resistance of 5 ohms. We have information about the step-down transformer at the end of the transmission lines. And finally, we have information about the load as well. So there's 5 sections of this transmission system we need to consider now that we're looking at scenario B. Now the first question we're asked to solve is to calculate the current in the supply. This is exactly the same as the previous scenario A, so I've left that answer there as 41.67 amps. The second question is to work out what's the voltage drop in the transmission lines. Now to solve the voltage drop, as we did in scenario A previously, we simply take the current running through the transmission line and we times it by the total resistance of the transmission line, which was 5 ohms. To calculate the current in the lines, we need to consider the effect of the first transformer. We're starting with 41.67 amps leaving the power supply. It then enters in a very short distance a transformer T1, which is at 1 to 10 ratio, a step-up transformer. So we need to work out what is the current in the second coil of this transformer. So in order to calculate the voltage drop, we need to calculate the current in the lines. The current leaving the supply is 41.67. It is labelled by 1 as it enters the first turn of the transformer. We want to calculate the current in turn 2 of the transformer as it exits into the transmission lines. We also know the ratio. N1, the number of turns in the first coil, compared to N2, the number of turns in the second coil, is a 1 to 10 ratio. Let's now use an equation to calculate I2. Here's our starting equation. The ratio of the currents in coil 2 to 1 is equal to the ratio of the turns of 1 to 2. Let's now solve for I2. There we have it. The current enters the transformer into coil 1 at a value of 41.67. It's a 1 to 10 ratio in terms of turns, so it's stepping up the voltage by a factor of 10, but it's stepping down the current by a factor of 10. So we started with 41.67 amps. Once it exits the transformer, and we measure this across coil 2, we find we have a current of 4.167 amps. We can now substitute that value into our equation to work out the voltage drop. So there you have it. When you multiply the current running through the transmission lines by the resistance, we have now a voltage drop with the transformers installed of only 20.835 volts. Our next question is to work out the power loss in the transmission lines. So there you have it. The power loss in our transmission lines is the current that we just calculated of 4.167 amps squared multiplied by the resistance of the transmission lines of 5 ohms. That gives me a power loss now of only 86.82 watts. We're now asked to work out what is the voltage at the load. Now there's many changes to voltage in this system. First of all, it exits the power supply at a voltage of 240 volts. We then enter the transformer, which steps it up by a factor of 10. We then have voltage drop in the transmission lines. Then we hit the second transformer, which steps it down by a factor of 10. And then finally we have our load voltage. So there's 3 steps you need to consider. Let's look at these one at a time. Let's consider what's happening with the voltage at transformer 1. Let's now consider what's happening at transformer 1. We have voltage 1 in the first coil of 240 volts. We have a voltage 2 exiting the transformer in the second coil, which we're trying to calculate, and we know the ratio of turns N1 to N2 is a 1 to 10 ratio. Here's our equation. Voltage in the second coil divided by the voltage in the first coil will be equal to the number of turns in the second coil to the number of turns in the first coil. We now want to work out what is the value of V2. We know the value of the voltage 2 in the second coil will be the first coil's voltage of 240 multiplied by a ratio of 10. We know that N1 over N2 is a 1 to 10, so N2 to N1, the reverse, is a 10 to 1. So we're stepping up from 240, we're multiplying it by 10 to give us an output voltage in the second coil of the transformer of 2,400 volts. That's step number 1. We can now use the voltage drop that we calculated earlier in our transmission lines. So we start in the transmission line at 2,400 volts and we lose 20.835 volts. That allows us to work out what voltage is entering into the second transformer. So let's write this down in step 3. So in this scenario, we're looking at transformer 2, the step-down transformer, the 10 to 1 ratio. We know at transformer 2, the voltage in the first coil will be 2,400, which is the output of the first transformer, minus the voltage drop in the wires, that being 20.835 volts. When I subtract that from 2,400, I end up with 2,379.165 volts. And I want to work out what is my V2 coming out of the second transformer. And we know the ratio of N1 to N2 is 10 for this step-down transformer. Let's now use our equation to solve the value for V2. Finally, we're asked to work out what is the power that reaches the load. So the power that reaches the load is our 10,000 watts at the start, our 10 kilowatts, minus the power loss in the transmission lines of 86.82 watts, which gives us a load power of 9913.18 watts. Once again, we could express this as a percentage loss. So the percentage loss of power with this transformer scenario is only 0.8682%. Now, comparing our two models, that was scenario A without any transformers and scenario B, which you can see in front of yourself at the moment with transformers, I want to have a look at the various measurements made. So first of all, in scenario A without transformers and scenario B with transformers, applied current was exactly the same, leaving our power supply. Let's now consider the voltage drop in both scenario A and scenario B. As you can see, there was a massive drop in the voltage for scenario A. Nearly all the 240 volts from the power supply was lost in the transmission lines, whereas in scenario B with the transformer, we only lost 20.835 0.35 of a volt. That's a 10 factor difference. It's because the voltage drop is proportional to current. If you recall, when we used our step-up transformer, we effectively dropped our current by a factor of 10. Because our current was reduced by a factor of 10, so was the voltage drop. Let's now consider the power loss in both scenario A and scenario B. Again, a massive difference. This comparison was a factor of 10. If you look at the power loss, it's a factor of 100. And that, if you consider the equation for power loss, is quite understandable. So the equation for power loss is P equals I squared R. When we reduce our current by a factor of 10 in scenario B, we effectively square that change and our power loss will go down by a factor of 100. 100 times less power loss in scenario B with the transformers. And this is the benefit of why we use transformers for long distance power transmissions. We want exceptionally high voltage in order to reduce our current and produce low voltage drop and low power loss. Let's now look at what impact this has on the load voltage at the end, our destination of our transmission system. In scenario A, with transformers, we start with 240 volts, and of that, only 31.65 volts actually reaches the load. The rest is lost in the transmission lines. In scenario B, with the transformer pair, stepping up by 10, stepping down by 10, of the 240 volts we start at the power supply, 237.92 of those volts reach the load. This is a great outcome, much, much better. Let's now consider the power that reaches the load. Again, without a transformer in scenario A, the original 10 kilowatts, 10,000 watts, is transferred across the distribution system, and of that, only 1,318.06 watts reaches the actual load. Whereas with transformers, the stepping up and the stepping down, the 1 to 10 and the 10 to 1 ratio, of the 10,000 watts that we started with from the power supply, 9,913.18 of those watts reaches the load. A lot better return. Finally, as a percentage power loss. Once again, as a percentage, when we have no transformers, we find that 86.82% of the power we started with is lost in the transmission lines. With the step up and the step down transformers, we find that less than 1% of our power is lost in the transmission system. The takeaway message again is, if we have long distance transmissions, we need to step up our voltage for the long transmission lines, which in turn reduces our current. Low current in the transmission lines will directly reduce our voltage drop, and the power loss in the transmission line is proportional to the current squared. So reducing it by a factor, say, of 10 will reduce the power loss by a factor of 100. It is optimal to transmit over long distances at high voltage and therefore low current.